We're going to talk about the isentropic efficiency, which is, for instance, the ratio, and this is, for instance, for a turbine, is the ratio between the real work that performs the turbine over the isentropic work that the turbine might have. And this is, for instance, we're going to state it. Now, the real work, for instance, in a turbine, since we're getting rid of all the kinetic terms and potential terms and all of these terms, we have to remember that the real work has to deal with some change in enthalpy with some heat. And for instance, we can state this is going to be, for instance, H1 minus H2, and we're going to plug here an A, which is, for instance, the real state of the exit at the turbine, and we're going to here put H1 for the isentropic work minus H2 at the isentropic way. So, for instance, what are we talking about? If we talk, for instance, in this situation where we have a diagram of enthalpy with respect to entropy, and we're talking about the ideal way, no heat is going to be lost during the process of compression in the turbine. We're going to start at a certain pressure, and then we're going to go in a straight line like this in an isenthalpic way. And we're going to go, for instance, from the H1, where we start the process, to, for instance, H2S. That could be, for instance, the ideal way of doing this. But in real life, certain entropy is going to be generated. So since we have to generate some entropy, then the actual process has to go somewhere like this in order to get to pressure 2. So in this case, for instance, we're going to state that this is H2A, right? So the isentropic efficiency, well, you might actually see that since H1 minus H2A is smaller than H1 over H2S, this has to be lower than 1. This is called, for instance, the isentropic efficiency of the turbine. For a compressor, for instance, the work is the other way around. And this is, for instance, the isentropic work over the real work. And we can actually do the same diagram, right? And we can actually do the same analysis. Or, for instance, we have P1 and we're going to compress this towards a point of P2. And in an isentropic way, this would be, for instance, something like this. But real life is, for instance, a process like here. So since this is an SH, well, this is, for instance, H1, right? For instance, H1. This is, for instance, H in an isentropic way, we're calling it HS, and this is, for instance, H2A. So this entropy, or this efficiency, isentropic efficiency, is going to be equal to H2S minus H1 over H2A minus H1. And this has always to be less than 1 because this is an efficiency. And this is the isentropic efficiency of a compressor. For a pump, this is exactly the same. The work which is isentropic, right, over the work which is, for instance, real, and this is going to be, for instance, the isentropic work is V P2 minus P1. This is not taking into account any potential energy, kinetic energy, or actually heat over the real work, which is, for instance, the actual change in enthalpy, which has, for instance, the process done in the pump. So we have discussed the isentropic efficiencies here.